Okay, yesterday what we did was to show how I could algebraize geometry to some extent. Now there is, of course, the main objects in geometry, well, one of the main objects and important objects are manifolds. Now, manifolds are usually described in with points, because it means that I have a space, I can cover it with charts, and charts are maps into Rn, points there, and then I have transition function and everything that makes a manifold. So a manifold is not only a space, but with a smooth structure. Okay, so not only continuous functions, but smooth functions, and I can have differentiability. So I should be able to translate this using my tools, which are algebras, Hilbert space, and an operator. But it turns out that to do that, from a purely mathematical point of view, I need two more operators. So really the spectral triple has become a quintuple, if I want to talk about operators. And very interestingly enough, I wanted to ask one thing. How many of you are mathematicians? Okay. And the rest are physicists? Okay. So I will try to give some quick explanations of what I will do. So, now from the mathematical point of view, I need two more operators. One I call the chirality operator, is a grading, and this is necessary for mathematical reasons. In fact, it comes out mathematically, and it's an operator which I call capital gamma, with a square which is 1. It exists only in the even case. It actually defines the even case from the mathematical point of view. And since it's an operator whose square is 1, the eigenvalues are plus or minus 1. And it splits the Hilbert space into two parts, which I call left and right for physical historical reasons. And then I need another operator, a charge conjugation operator, I will call. It gives what is called the real structure, and is an operator which is anti-unitary. There are not that many anti-unitary operators. In fact, basically, turning around is only one. Complex conjugation and some inversion. And for us, this is the charge conjugation, but we are in the Euclidean, so you know, when parity and time reversal just get together. So charge conjugation is also there is charge conjugations and then parity time reversal on the other side, and the two together are the identity, because here is sensitivity variable. So for those of you that know what it is, and I will not describe it, it's connected with the Tomita-Takesaki operator, which is always this charge conjugation, is anti-unitary operators.
So what do you mean real structure?
Is a definition. If you have J, then you can recognize a real structure, which somehow it splits into a real and imaginary part. But it's just a name. Okay, so a real spectral triple has this object. An even spectral triple has this. The reason for this is that in physics, you can only define well gamma 5 if you are in even dimensions. In odd dimensions, you cannot define. And the real thing is that this is like I. No? So if you have an I operator, then there are things which are invariant, which don't contain this. So you can recognize what is real and what is imaginary. Okay? So but at this point, there are just two names. And there are 7 conditions. They are often called axioms because they started with as axioms by Kohn, as a sort of conjecture. And then later on, Kohn himself proved that the reduction of this to the commutative algebra defines a manifold. So this is what will define a manifold for me in this context. So the first, I will go through them not in great detail, but some of the things are important. First one is dimension, okay? A manifold has an integer dimension. And I discussed the dimension before.
Yesterday you discussed the dimension in terms of the spectrum of the Laplacian operator.
Yes. Yes.
Can you write down in terms of the spectrum of the Dirac operator itself?
The Laplacian is the square of the Dirac
Yeah,
operator.
but can you rewrite, just recast it?
Yes, the same thing. I have to put, the eigenvalues are the same. I have to put an absolute value. The eigenvalues are the square roots, the positive and negative square roots. The growth is the same. They are not completely the same if there are boundaries and something, but I can do the same thing. And the formula is slightly different.
The Dictionary's theorem tells you this apart from Laplacian also curvature term.
Yes.
That don't disturb it.
No, because the dimension is always an ultraviolet phenomenon, and a manifold at very short distance is always flat. It doesn't matter. So a curve thinks sometimes. But if I am small enough, no matter what the curvature is, it will be always flat.
Yeah.
And the dimensions see the tangent space.
Yeah,
And the tangent space is always
locally
flat. So it's locally flat. So the number of dimensions is well defined. So it has to be. So in order to have a spectral triple, which is a quintuple, I must say that the dimension is well defined. So I can take the Dirac operator or take the square and see if it's well defined. Okay. Otherwise, it's a non-commutative space which is not a manifold. Okay, it can still exist, but it's not a manifold. Then regularity. This is like smooth, looking for smooth functions. So I take an element of the algebra, and I should have that both A and the commutator of A should belong to the domain of delta. Delta of K is a power. Delta means just taking more and more commutators with the real positive part of the operator B. So this is smooth. No? A smooth function is something that can derive an infinity of times. So in these terms is that if I derive the function which I obtain must be in the domain of this. So when I take this function, it makes sense to derive it once more, and once more, and once more. So it means that I can derive an indefinite number of times. So they are C infinity functions. Then, this is more technical. If I take the domain of the operator to the power k, and I take the intersection of those, so I act with the Dirac operator as many times as I want on the space, so the domain of this operator must be a left module for A. So the algebra should act on vectors of the Hilbert space as many times as I want, and should be finitely generated. Let me skip this concept that probably is known to mathematicians, but it's so it's a restriction on the domain of this operator, which means that if I take a spectral triple, I cannot take any Dirac operator that I want. So in fact, Dirac operators must be a derivations if there is a continuous structure. So it is imposing restrictions. Then reality, this is an important one. That there exists this operator anti-unitary J with a commutation relation fixed by the number of dimensions. So J should commute or anti-commute with gamma, with D, with all this, and it must be of this kind. Now this is an important one. This is an element of the algebra, and I want to take the commutator with this sort of elements for any element of the algebra. So I take the algebra and I conjugate this by this operator. Okay, this is called the opposite algebra, and in fact below I call it the I call it BO because it's the opposite algebra. Now the algebra with these objects, see, they are all operators on the Hilbert space, so it makes sense to make commutators. It should commute. Okay? We will see this, that this is like acting on the Hilbert space from the right rather than from the left. Okay, so this is the meaning of this.
So the module should be bimodule.
It should be a bimodule, really, and the two actions should commute.
Yeah.
Okay, so it's like, so if it's finite dimensional, it means that given a matrix, and I should act two ways. If I have a matrix and a vector, I have two actions. I get the usual one, conventionally, I multiply row by column. But in principle, I could multiply column by row. And this means it's multiplying the dagger on the other side. Of course, those two commute, because I take a vector, I multiply in the usual way, and I obtain another vector. And I act on the other side. The two actions, it doesn't matter which one I do first. Okay, so the actions commute. So, and the same thing happens not with the elements of the algebra, but with this, which you will recognize as one forms. Okay, so, and this will be a strong restriction. Then orientation. Orientation is, the grading was capital in the previous page, now it's become small, but there is a grading, and this grading should be related to a Hochschild co-cycle of degree n. Now this is, for the physicist, this is a form of highest degree. So dx0, dx1, dx2, dx3, or whatever dimension. So this must be a full thing. Now you remember that I was connecting the forms with the gamma matrix. Dx mu was gamma mu. So now if I put everything together, I get gamma 5. Okay? And this is telling me somehow this. Okay? It's telling me that it should exist, this object, and it should be gamma 5. Okay, so the grading. So I'm putting in completely algebraic terms the requirement that you have a gamma 5, which is not automatic in a theory. A manifold should be even to have a gamma 5. Otherwise it doesn't work. This one, let me skip. The Poincaré duality, doesn't play a role at this point. It's the duality between one forms and three forms. No? Because it means that you have a epsilon mu nu sigma rho for a physicist. It's a
Hodge dual.
not really. But this is a duality between n and n minus 1 form. It's not, the Hodge duality is between forms and vectors. Okay? So for this one you need a metric, but we have a Dirac operator.
No, Hodge dual takes you p form to n minus p form. That you contract with, suppose you take a p form and contract with the epsilons with n indices, then upon contraction it will result in n minus p. Or if p is equal to 1 in particular, then you connect from one form to n minus 1.
Okay, this is the Poincaré duality connects forms, n forms with p forms with n minus p form. But it doesn't work. In any case, now I don't want to. This doesn't play a role, so I can happily skip. Otherwise, instead of putting mathematicians and physicists, yes.
What is the K theory of K in the Poincaré K theory of?
Yeah, K theory is K theory is the properties of algebra or spaces. Based for the algebras, they are properties of the projectors that you have on them. They are a very powerful tool to classify spaces. Okay, and classify algebras. And they are based on the structure of projectors. And they are very important for mathematicians, and they are very important for people in string theory as well. But they are not very important for the next 3 lectures, so I will skip it, if you don't mind. Otherwise, it will take. Okay, so.
In the point 4, so how J is fixed by the number of dimensions?
No. With the commutation relation fixed by the.
This dimension will be KO dimension, right?
with the number of dimensions. Then which dimensions it is, I will take. J and gamma. So J gamma must be something like gamma J. JD and all of these operators will have to have a commutation or anti-commutation relations where epsilon, there is epsilon and epsilon prime, they are always plus or minus 1. Okay? So I have this J, and this J must either commute or anti-commute with gamma, with D, and with everything, with coefficients which depend on the number of dimensions. Okay, so J is a datum of the problem. You are given, saying that when you do a physics problem, say, let's take a particle on a de Sitter space with a certain metric. Okay, so this is the datum of the problem. I want to be algebraic. So I will not give you a space, I will not tell you what the points are. I will give you an algebra, I will give you a Dirac operator, and I give you an Hilbert space. So instead of taking a fermionic theory on a de Sitter space with metric, blah, 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 and the fermions which change in some way, I will come and I will give you the datum which is all algebraic. One of the datum is the algebra, no? I give you a hyperboloid with a metric which will be. Then, in my case, I can come and instead of give you an hyperboloid, which is topologically just an Rn, I give you a non-commutative algebra, which doesn't correspond necessarily to an hyperboloid, but this is your space. So they are always datum of the problems, but in order to be a manifold, they have to be consistent with each other. So you cannot put an arbitrary metric. A metric tensor is a matrix with points, but it's not any choice of functions with matrices will make a metric. They have to be at the same way. I cannot give you random Dirac operators and algebras. They have to satisfy conditions, and if they satisfy these conditions in the commutative case, of course in the commutative case these are not there present, but if they satisfy these conditions in the commutative case, then the object is a manifold. So I don't give you the charts and everything. I give you this spectral data. So see, so the one has to think always in terms of algebra, spectrum, and operators and something, because this will enable you to generalize things. And now let me go to the second lecture, except that. The name is Corfu, but I looked at them. It's not exact. I'm not repeating exactly the. This is the full screen, no?
Control A.
Control A. I am a Mac person, so. No, that is for the view. Full screen. Okay. Okay, now let me go on and let me start describing the action. Action is the integral of the Lagrangian, and is what gives you the dynamics of something. So if you have a dynamical system, it means that you have a state of your your physics, and then you evolve it, for example, in time, or in the case of quantum field theory, you can calculate the partition functions, scattering amplitudes, and everything, starting with the action. You put it into a path integral, and you do the quantization. So, in the easiest case, you have a free field, okay, a free boson, a free particle, or a free photon. You put it in the action, and that tells me how the object is propagating. Now, if you are in flat space, that's easy. It will go on a straight line. How long it will take and how it will interact with other particles. If you are in curved space, then it will move down something. We are aiming at quantum field theory, so they are not just particles, but they are fields, they are distributions. So action is what makes physics at this point. So far we have done geometry, and now we have physics. So, so I want to apply this to quantum field theory. I want to do this because the theory of interaction, of fundamental interaction, strong, weak, and is a theory of fields. It's not a theory of particles, although we are very happy that we found the Higgs boson particle, but the Higgs boson is really a field, because in quantum mechanics there are no particles, there are wave functions. So now I'm explaining to mathematicians why the next lectures are based on the action, how the action comes out. Now, the mathematics which I introduced is geared for such a task, because we have the ingredients to write down the classical action of a field theory. Because field theory has an action which is based usually on Laplacians or Dirac operators, and an interaction. So I want to know what happens to this field when it meets another fields and those interact. And the states are usually vectors in some Hilbert space or Fock space or something of this kind. So now for free, we have the ingredients to do physics. And here this is a disclaimer for physicists, because I will be in the Euclidean and compact space-time. Euclidean I need because I need elliptic operators, and the compact I need because I need a discrete spectrum. Now, these two are different gravity, not gravity, seriousness from the physics point of view. Because compactness, it means, well, space-time is non-compact. So we have to put a boundary to this. This is called an infrared cutoff. So we cannot go to arbitrarily large distances. In general, but there are exceptions, but in general in physics, this is an armless thing, because since fields go to zero at infinity, somehow I don't really care what happens afterwards. If you have a black hole around, things are very different, but it's considered not a grave sin. This is more grave. This is more serious.
What is is there any mathematical definition of compactness of a space-time?
There is a mathematical definition of a compact space. And there is a physical definition that tells you that the space-time cannot be compact. So you have to compactify space-time. And so you put just your particle in a box. Okay? And what I'm saying is more serious is Euclidean. So I don't distinguish time from the other directions. In particular, I don't put a minus sign, which means that my Dirac operator and my Laplacian are elliptic operators, and they are not hyperbolic. Now, this is serious because, of course, in physics we need time. Otherwise, time is very different. I'll come to you. It's very different as a direction, and therefore it's a very serious thing. However, this is not an unknown situation. Several field theories are used in the Euclidean case, also because the Euclidean case is very good, because some divergences in the calculations, there are infinities which come up constantly. If you are in the Euclidean case, these infinities are not infinite, because some integrals, basically e to the I something becomes e to the minus something, so instead of being an oscillating term, which will be infinite, will go to zero. You had a question?
Yeah, my question was about that compactness and mathematical definition of compactness.
Is the algebraic definition of compactness?
No. I forgot my question.
No. Compact is the definition of a compact is the one that we know covering as a finite subcovering or it basically it must have a boundary.
Yeah, I mean,
So it's the usual.
I had
It's
a
the
different
usual.
question.
It's the usual. But if you are
Yeah, yes.
with a Laplacian,
Yeah, well, elliptic operator, you said.
Yeah.
What is that elliptic operator?
elliptic operator it has all. So the Laplacian with all pluses is an elliptic operator. If you put a minus, becomes hyperbolic, because if you put a zero, becomes parabolic. Now the definition of elliptic, I don't remember, but it's probably pretty sure.
It's a bit complicated. So these are certain differential operators, and then you can define something called a symbol.
Yeah.
And then,
The symbol, symbol is a vector, and the eigenvalues of this vector, they have to be all positive. Okay.
This is definitely different from linear operator. This does not.
They are all linear operators.
They're all linear operators.
They are linear differential operators. Okay. Now there is a symbol of the differential operator which is the coefficients of the highest level, and they are a polynomial. Okay. Now this polynomial can be an ellipse, or can be a hyperboloid, can give you, it's an it's a polynomial, so it gives you a surface in a certain number of dimensions. This surface can be compact, and it's called elliptic, because if you are in 2 dimensions, it will be an ellipse. Can be an hyperbola, or can be a parabola. And so this is the kind of surfaces. I think this is actually the definition. Now it's remembering. Yes?
And I was asking, are these notions related, Euclidean and complex space-time?
If they are related with each other. If I'm not Euclidean, I have difficulties in defining compact. Things can be done, but one has to define Krein spaces, and things have become more complicated than
So
the
if
recent.
you go to non-compact space-times, you will not have like elliptic operators
No, in a non-compact space-time, you can have elliptic, hyperbolic.
as well as hyperbolic.
Yes, but what I need is discrete spectrum. So if either of those is missing, I cannot have the discrete spectrum. But even mathematically, there is a big difference. One thing is to have a continuous spectrum of an elliptic operator. So I will have, in the spectral decomposition, which is always there, the spectrum is itself a joint will be on the line. So I will have a measure. So if it's discrete, I have an obvious measure. I sum the eigenvalues, counting with degeneracy more than once. If it's continuous, if I have to take the sum of the eigenvalues, becomes an integral. So I have to put that density. And I have a density which is coming from the spectral decomposition theory. Things becomes much more complicated, and I don't know really how to deal with them. But being compact is not a big problem. The Euclidean is more serious, because physics is with time. Time is I was telling dynamical system is something that moves. If I don't tell you what is time, things don't move. But field theory I can do the Euclidean, because field theory is just I write an action and I quantize by doing sum over all the configuration in a path integral. So I actually, field theory is much easier to do in the Euclidean context. Okay, but here I have to be Euclidean.
So if
Okay.
you go to non-Euclidean, which is, can you construct compact space-times there?
Non-Euclidean compact. Yes, but probably it will have some closed geodesics, no?
Non-Euclidean complex.
non-Euclidean.
So that's
Yeah.
where
Minkowskian compact.
concepts are
Minkowskian
so
compact.
you cannot mention Euclidean.
Minkowskian compact.
Oh, yes.
So time will be
Notion of
compact.
compactness, then
Yeah, but then you have,
if you say Minkowski,
yeah.
you will end up with
Yeah,
non-compact.
you can do it, but you will have a paradox of closed time-like curves, no? So everything will, because if it's compact, you just sit without doing anything, and sooner or later you will come back to you, no? Because or you can put measures, but in any case, don't blame it on me. There are a distinguished body of field theory which is Euclidean and compact. I'm not the only one. There are books and books, and people do Euclidean quantum field theory because they cannot do the Nicotian one because of divergences. So it's not. Don't blame it on me. It's present everywhere. Okay, now, in order to do this, I want to do a system, and I want to know what are the matter fields. They are, because I'm going to describe particles, they will be functions, they will be fields, but they will correspond to the electron, the proton, and everything. And what I do, they will be members of a Hilbert space, and I have a Hilbert space because I have to represent my algebra on the Hilbert space. I can do it with a reducible representation, and I will identify these elements of the Hilbert space with the fermionic matter fields of the theory, and I will be more precise I will describe what those are, okay? They are the usual particles, and I will describe what they are. The electrons, the muon, and so on. Now, the Dirac operator, which I give, and I call D, may fluctuate to give some covariant operator. Because Dirac operator is something which depends, should counterbalance gauge transformations. Now, everything is a gauge theory, both the field theory of particles, but also gravity is a gauge theory. In one case, the group of transformation are the gauge group of the weak force and the strong force, and I will say something later on. In the case, the general relativist diffeomorphisms, but they are gauge theories. So there are degrees of freedom which are spurious. They are not really physical, and I have to compensate this by adding a Dirac operator, which I say fluctuates. I have to add a connection form to it. Or for physicists, I have to add a potential. But I know what a 1,4 is. And it's an Hermitian 1,4, which we physicists would call a potential, which is a generic element of the form, because I told you what the 1 forms were. They were the commutators of D with the elements of the algebra. So this is the most general 1,4, and these are two generic elements. Later on, I will take into account antiparticles of the J, the real structure. For the moment, this is just this. But now, this is something which is important for physicists. If I have, in general, I can come and I say, let's take a field on some space, and then I give you which metric there is, and then I tell you what the potential is. So if I'm describing interaction of a certain kind. Here, if I give you the Dirac operator, automatically I am determining the kind of potentials which I can have. In physics, this is something which is, I can choose whatever I want. But here instead, no. If I give you the Dirac operator, I know what interactions there are. If I give you the Dirac operator and the algebra, okay, the elements of the algebra.
By potential, you mean
1,4. Okay, potential 1,4. Okay,
self-adjoint.
it's a self-adjoint 1,4. Self-adjoint because the Dirac operator is self-adjoint, so I have to add the self-adjoint 1,4. And self-adjoint 1,4s are determined without problems. I forgot my watch in the office. Without problems, but without ambiguity, by the Dirac operators and the elements of the algebra. So I can. Those are the only potential connection 1,4s which I can view. So everything is in the data which I'm giving you. So A gives you sort of the space-time, the algebra gives you the space-time, but gives you also the gauge potential. And there are two important exercises. We'll do them if we have time. They have a historical role. Now, what happened was the following. really Alain Kohn told me that he was doing these things, and he started to do the most simple algebra that you can think of, or the second most simple sister algebra. The most simple sister algebra is complex numbers. Okay. Now, the second most simplest is two copies of these complex numbers. Topologically, this corresponds to 2 points. Discrete, 2 points are both open and closed because C2 is a commutative sister algebra. So my topological space is made of 2 points, and it's with a discrete topology. They go open and closed. And I can represent these two as diagonal matrices on this algebra, Cm plus Cn, so multiples of the identity. And the Dirac operator doesn't look at all like the one introduced by Paul Dirac, because since this is the Hilbert space, I need an operator which will act by commutation, and so it must be something like that, where M is a rectangular matrix, and you have to find A. Okay? And you can also find, as an exercise, curvatures, 2 forms. Now, the whole thing started because Alain did this calculation and found that the potential which was emerging as a 2 form, okay, there's a 1 form potential, then you can calculate the curvature of this. The potential was basically a 0-dimensional version of the X potential. Okay, so as a mathematician, no, like I can chastise you, mathematician. He knew what the X potential was, but on the other side is Alain Kohn, so he knew lots of things that all of us put together will not know. So he was playing with matrices, like everyone of us does, in the simplest possible thing, and he detected this this connection of the connection between the connection of 2 points and the connections which is given by the X field. Then you do the generalization, in which instead of having 2 points, you have 2 copies of a manifold. So you take the product of the 2 points, which is Z2 topologically, and this Z2 is not integer number, it's just 2 points. And then I multiply times a manifold. This is still a commutative algebra. So it's 2 copies of the functions on some manifold, some variety. And again, I represent the Dirac operator, but this time it will have a part which is this df, and it will have a part which is the usual Dirac operator, the one done by Paul Dirac. So I have one continuous part, but then at each point I have actually 2 points, so I can see it as a 2-sheeted manifold, or I can see it as a manifold with the 2 points, each point split into 2. Now I have a part of the connection which is the usual one, so the manifold will be curved, and another part which is a finite part. The presence of this gamma pi is really for technical reasons to ensure this kind of commutation relations. And if you do this, then you do really find the curvature is the X potential.
Sir, can I say the first exam exercise, the TF is a mass matrix?
Yes, this
is a mass term.
This gives the mass term in the fermionic action. So this is
that is why the X potential arises.
Mm-hmm.
The psi bar
That's how the X potential arises. Historically arose. From the spectral action, it will come out in a slightly different way, in a heat kernel expansion or something, but really conceptually, this is what happens. If I have this very simple, you can think of these 2 parts like the left and right chirality of fermions. Okay, so the whole Hilbert space is split into 2, And all particles are left and are right helicity when they move around. Again, physicists will forgive me, this is the equivalent of the thing that I said with the eigenvalues before, but a particle moving always has an intrinsic angular momentum. So this can go towards left, right, or right. So they are left and right. The same particle will have a left and a right version. Neutrinos may have only one, and we'll discuss this a little bit later. And this is like
what is this df in the second example? What is df in the second example?
The same as this one.
But there is no Cm plus Cm. Right?
There is
Where
no?
does it add? Why does df?
Is there a direct sum in the
Yeah.
near term?
Gamma phi tensor df.
Sorry, H is, this is tensor.
That should be-
Yeah, you're right, you're right.
And there is something, the Hilbert space.
The
has
Hilbert
to
space must be
amplified,
the
right?
tensor of this times this.
Then it's okay.
So the Hilbert space, so it will have this. Yeah, he was correctly noticing that df acts on this Hilbert space, and this acts on this Hilbert space. So in fact, the Hilbert space should have written as I did, as two components, two parts, and the Hilbert space will be two parts, will be this times this. So this part, so really the Hilbert space is
Gamma. What are the grading term?
the Hilbert space will be L2
No, it's you.
of M times G. What I call the first one is M plus L2 of M times Cn. Okay, so this is the left-handed fermions, and with components which are in principle different. Okay, so I can do SU2 cross U1. That's what he was doing. So this one was two components. This one was one component. There were no right-handed neutrinos at the time. And so this was two and this was one. And it was, the curvature of this is the bosonic part of the action, which means that is the two F mu nus, the two interaction of W's and the B and the X field. So that's what historically what happened. But for us, the important aspect is that when you fluctuate this thing, there is,
D also should be gamma phi tensor df. Tensor gamma phi.
yes, again, yes. Yeah, this is O times and not O plus. And this is a plus, yes. So there are two mistakes on one line. I managed two mistakes on one line. I can get to three without problems in due course.
Sorry, I have another question. So,
Yes.
yeah. So by a scalar field, do you actually mean a function on n?
Yes.
A good function
Yes.
on n.
Yes.
Like, if I get a one form of this spectral triple,
Yes.
so then how do I get this scalar field?
When we do the exercise, I'll show you if we do the exercise, if I have time. Otherwise, I can tell you that the fluctuations, it's relatively simple. You have to take the commutator of this times a diagonal matrix. So an element of the algebra So let me concentrate on this part. Okay? Now, the Dirac operator I can write as a matrix. D will be something of this kind. D slash, M and M. And I have to fluctuate against two particles, lambda 1, lambda 2. So this is a complex number, and they are functions of x. Okay? Now I have to take the commutator of this with this and multiply by another element of the algebra, which is a lambda prime. Okay? Now this is just cranking a machine, 2 by 2 matrices. I made a career by multiplying 2 by 2 matrices. In the end, your connections will be something of this kind. Your A, you have to be self-adjoint. It's 2 by 2 matrices, but a doctoral 2 by 2 matrices. It's not completely, but you get something like that. Here you get this slash plus A slash left. Here you get this slash plus A right left. They will have indices which are due to the fact that this is a n by n and m by m and diagonal. So on the diagonal part, you get the covariant Dirac operator, which corresponds to a gauge theory. This is the gauge connection, corresponding to, if it's a U1 theory, this will be the photon. If it's a SU2 theory, this is what will be called the W particle. If it's a SU3 theory, this is what is called the gluon. Okay? Left, but this here I'm doing SU2 cross U1 for physicists. So this is the W, and this is what is called the B. And on the off diagonal, so those are functions. I have to do something, and on the off diagonal, you get an object without indices. There were no indices here, which I call phi. Okay? Now, this is the X field. Okay? And when I do the curvature of this, which I can do with the techniques of non-commutative geometry. So if I do the curvature of this, what do I find? I find let me call something F. Now physicists will recognize I will find W mu nu, where this W mu nu is d mu a nu minus d nu a mu, and if it's non-abelian, there will be here a mu a nu, and here there is some coupling constant G. Okay, so this is the field, the electromagnetic field of this generalization to the non-abelian case. And I find two of them, of course. Here I find W, then from this one I will find D mu nu, the one corresponding to this interaction, which is given by this. And then here I will find phi squared minus a constant, the whole thing squared. So here there are other terms. This is the X field. Okay? This is a field. It's a scalar field because it doesn't have any index. A mu, it has an index. So under transformations, under Lorentz transformation, it's constant. So it's in the trivial representation, so it's a scalar. And it has a potential, which tells me how it's. And this potential is the one, the X potential, the one introduced by X and Lair and Braut. For physicists, this is it's a very important thing, because in general we consider as completely different objects the W, the Z, the particle which correspond to the interaction. Okay, they mediate the interaction, and the X field is a vector, is a scalar. Those particles are called vectors, and we do recognize that the photon, the gluon, and the Z are the same family, and we call them intermediate vector bosons. Here the phi is an intermediate vector in inverted comma boson. Why is not a vector? Because the vector characteristics are the ones which are given by the manifold, and we are given by the two sheets. So on the continuous part, they are the fluctuations, the vibrations of the fields on the continuous part. The x is the one which relates to the discrete part. So it's like, it's vector, but it's the component in the continuous part. As is by vector, we mean the usual coordinates. So it will look like a scalar, but really is the component in the, so this is, now for physics, this is like a discrete Kaluza line. In fact, Kaluza line is when you have an internal dimension, and for example, the original Kaluza line, the electromagnetism connection was part of the gravitational connection, was the internal part. And of course, strings have too much of this because they have lots of things. So historically, this was the first time that there was a connection. This was in 90, I think in 90, probably original things, 89, 90, the original paper by Kohn and Lott. Notice this was in 91. So now this is somehow lost because I will make things appear in a more serious way with a spectral action. I will do other things. But fundamentally, this is the idea. The idea is that you have a manifold, which may be a non-commutative one, or in this case it was also commutative, with an internal structure at each point, which is described by an algebra. And then you have the possibility of having connections moving around the fiber bundle. For mathematicians, this is a fiber bundle. No, the gauge is the base of a fiber bundle on the basis, and there is a connection due to the fiber bundle of the gauge connection. But then you have a non-commutative part, and the fluctuations in the non-commutative part gives you the x. Now, if you do this, you write an action, and I can, of course, let me spoil the stories. When you do this, you get connections between, relations between the coupling constants, between the numbers that you have, and this enables you a prediction of the x mass, because things come naturally, and so this will enable confronting with physics. The prediction was not correct, otherwise Kohn would have won the Nobel Prize, that still things can be done. But so this is spoiling what happens tomorrow.
One more clarification.
Yes.
When you write Hilbert spaces L2M, it should be L2M comma S, no? It is a square integral spinors.
Yes, L2M comma S, yes. So there were 3 mistakes on the same time. Okay, this was actually, I wasn't thinking of saying too much on this, but, because I wanted to jump directly to the bosonic spectral action.
Sir,
Yes.
question from the teacher.
Huh?
So when you write the algebra, so
Yes.
is this what you mean by doubling of the algebra?
Yeah, Z2 is not, is just 2,
1 minus 1.
0 and 1, I mean, yes.
Z2.
Z2, yes.
So you write the algebra to be C0, the
Yeah.
direct product C0.
Yeah, 2 copies of
Direct
C0.
sum.
So is this what is mean by a doubling of the finite algebra?
No, this is a double sheeted manifold, so it's 2 copies of the same manifold. And the connection and I have 2 parts of the connection.